Hello and welcome. Today we are finishing chapter 26 of our textbook, which is Knight's Physics for Scientists and Engineers, and we'll be also continuing through some of the slides from chapter 27. Last time we took a look at the amount of energy that was stored in a capacitor plate between two capacitors, and we saw that we could write it one of two ways. We could write it as the charge squared per capacitance with 1/2, or we could see it instead as the capacitance times the voltage drop across the capacitor squared. So in any case, we have this kind of square dependence, and one of the example problems that we went through is actually we looked at a case where we took the voltage drop across the capacitor, doubled it to 3 volts, and we found that the amount of energy doesn't just become twice as much, it in fact becomes 4 times as much. So by that logic, you could also say, I'm going to bring up the camera here intermittently, that if the amount of energy stored in a capacitor is Q squared over 2C, you could also say something like, well, if I were to make the charge be multiplied by 2, this would imply that the energy stored would be multiplied by 4. Similarly speaking, you can say that our other definition here is CV squared. So I can say this is also equal to 1/2 C times delta V squared. This one here said that if delta V is multiplied by 2, the energy stored goes up by a factor of 4. So hopefully that makes sense. I'll put into some example numbers again just once more to make some sense. Feel free to fast forward the next minute or so if you already know this. Let's say the charge, for example, taking this equation over here, let's say that the charge is equal to 1 coulomb, and let's imagine that the capacitance is 1 microfarad. Well, in this case I can say that the charge is going to be 1 coulomb squared divided by 2 times the microfarad, which is 1 times 10 to the minus 6, and when I put this all together, you're going to see that I have 1/2 E6, or in other words 0.5 times 10 to the 6, and the units is going to be joules. So for example, that is 500,000 joules. That's a lot of energy. If I were to take the amount of charge and instead increase this amount of charge to 2 coulombs for the same capacitor, capacitance equals to 1 microfarad, then you can do the calculation again. 1 coulomb squared divided 2 coulomb squared, divided by 2 times 1 e minus 6, and you'll see that we have in this case we've doubled this. So actually I don't need to do the math once more. I can say that this is 4 times as much, and this will be 2 times 10 to the 6 joules, or in other words 2 million joules. Clearly you can see that these numbers are not realistic for the tiny capacitor that we had passed around in class, but nonetheless it gives you a feel for what the scaling is for these types of for looking at this formula here in terms of how much energy is stored. So the last question that we were confronted with here in our slide deck was taking a look at the total capacitance of this circuit. So I'm going to go ahead and copy down this circuit onto my page so that we can do a little bit more detailed looking at it together. So I'm going to write it, and then I'll switch to the camera mode here. So here we go. Okay. All right, good. So I finished writing it. Have you written it on your page? Maybe you can write that along with me, and we can take a look together. So here's what I have, and we're asked to figure out what the total capacitance is. So this might be our battery here. This is some delta V. If I want to combine these capacitors, I need to first group them together. So for example, I can see that these two here are in parallel with each other, and I know that capacitors in parallel, sometimes I'll write in parallel like this, they just add directly. So in other words, C total is equal to C1 plus C2 plus C3, C4, C5, whatever it is that if they're in parallel, they just add. For capacitors in series, they add in this kind of funny way. that the total capacitance is equal to 1 over C1 plus 1 over C2, etc. And we're going to take the inverse of that. So that to the minus 1 power is really important there. We need to make sure that we remember to add up their inverses, finally take the 1 over that number to get the total capacitance. So that's just a reminder of something that you saw earlier in the slides. Nonetheless, we can apply that here by recognizing that C1 and C2 are in parallel. So we should just use this first rule here. And I can say that this is the same thing as a circuit that looks like this. Here's my C3. We haven't done anything with that yet. But here's kind of a C total. I'm going to write a C total. I don't know. That's this C total here, in this case, is equal to C1 plus C2. Well, now we have a C total plus a C3. We need to combine these two capacitors, but they're in series. So we're going to actually add them together so that the C equivalent, let's say, is equal to 1 over this C total plus 1 over C3. And I'm going to take the inverse. So that's how we actually figure this out. And so then finally we'll be left with a situation where that is equivalent to just having one capacitor in my circuit, where this capacitor has the total value of 1 over C total, whereas C total is this thing here. So we can plug it on all in terms of the original values here. This is C1 plus C2 plus 1 over C3 inverse. And if we plugged in all the right numbers, then we would have the total equivalent capacitance. So let's just pick an example. Let's say that C1 and C2 and C3 are all 1 microfarad. Okay, maybe you can tell I like 1 microfarad. These are some kind of typical numbers. They're easy to work with mathematically. So then in that case, the C equivalent would be equal to 1 over 1 plus 1, which is 2 microfarad, plus 1 over 1 microfarad inverse. When I add 1 over 2 plus 1 over 1, it looks like I have, what is that, 3 over 2. And my unit so far is 1 over microfarad, which doesn't seem like it makes sense until we take the inverse. And we have 2/3 microfarad. And this is my equivalent capacitance for this circuit. That's just given the example here that I had this assumption that C1, C2, and C3 were all the same. You're being asked in a similar homework problem to do something similar, and I feel confident that if you understand this example, you'll be able to solve that problem. Okay, that concludes our work for Chapter 26. I welcome you to add questions in the comments of this YouTube video, and as well as questions for Chapter 27, and I'll try to respond to those quickly. So this moves us in a new direction here, where we're talking about current and resistance. In the lab, you've already had some experience with this, so we're going to move fairly quickly, but I'll fill you in on some of the theoretical details of how this actually works. We're going to learn how and why charge moves through a wire and what this meaning of current really is. So the picture that's in the front of your chapter, as well as this slide here, shows a light bulb filament glowing. And so you may not completely understand at this moment, why is it glowing actually, right? What is the reason? Well, the reason it's glowing is because it's warm, it's hot, and things that are hot produce light. Even you actually produce light, even though you're not nearly as hot as a light bulb filament. Another big surprise might be that to know that the temperature of the light bulb filament gets up to an extremely high temperature, almost the same temperature as the surface of the sun, which is 5,000 Kelvin. It's a very, very hot temperature. Now, it's not very big, so it doesn't produce a ton of heat, but if you touch the surface of a light bulb ever, you'll know that it's quite warm. This heat is the heat that's dissipated through a resistor. We'll get there, and we'll be able to talk about that. So we've talked about charging up a capacitor, and we might wonder, how does a capacitor actually get discharged? So the figure here on the left, figure A, shows two plates of a capacitor, and if we have them isolated from each other, a plus and a minus charge, we'll have an electric field in between them. And we're getting good at being able to understand the relation between the amount of charge that might be on here, the electric field, and the voltage. If you haven't reviewed that already, this might be a good time to pause and see if you can rederive what the electric field is, if you were given some charge difference, plus Q and minus Q, and what the voltage would be, and what kinds of pieces of information you need to know. Figure B shows a wire hooked up between these two. Now, if you just hooked up a wire, the charges would quickly equilibrate until you had the capacitor become neutral. In other words, there wouldn't be any buildup of charge on this capacitor. So, in the moment this wire is connected, there's a very quick motion of charges, and this motion of charges we call as current. In fact, you can actually even see, it's possible to see if there is a current by using something like a compass needle. And it turns out, this is something we haven't covered yet, but it turns out that a compass needle will deflect when there's current going nearby. And this is because wires that carry a current will actually produce a magnetic field. So we will get to a more detailed understanding of that soon, but I want to present that there is evidence for imagining that there is actually a current that flows. Additionally, if it flowed for a long time, it would actually cause this wire to get warm, or in the case for a light bulb, to get very warm and produce light. So the charge carriers, this represents what actually makes the charge move. And so as we've alluded to several times in this class, it's not the protons that move as part of the nuclei, it's the electrons, which are much lighter, and they in a metal, they're free, the ones that are free to move around inside of a metal. So the electrons, they become detached, right? So you can think of each electron as sort of orbiting around its ion in a metal, and somehow it's able to move around, and if there's an electric field, it'll feel a push. So the important part is that in a metal, electrons are the things that carry the charge. So sometimes you'll hear us talking about current is moving in one direction, and secretly it's really electrons moving in the opposite direction. And sometimes it doesn't really matter that we need to think of it this way, and occasionally it does. And I'll try to emphasize when it's really important to be thinking about it's the electrons that are the charge carriers. We define the electron current to be the number of electrons per second that pass through a cross-section of the conductor. So in other words, if you wanted to say to say this mathematically, perhaps at this point I'll move to the notes here. I'll say that this current here of electrons is the number of electrons that move per time. Okay? So we'll use maybe some of these things here. If you flip this around, you can see that it's this equation here, the number of electrons, the current times the time interval. And so this is electrons that are flowing into a wire. We want to go a little bit further here. We can actually see that the number of electrons is the density times the volume. That's one way you can write it. Remember that density is number per volume. So let me go back to the notes and write that here. So the number of electrons is going to be the number of electrons per volume. And I'm going to write this capital V. I'll put these little thingies on here to make sure that you remember that this is a volume, not a velocity. And if you want to think of it as that the volume is the cross-sectional area times the distance traveled. And if you want to think about a distance traveled, well, that's the drift velocity times the time. So maybe it looks like it's getting a little bit complicated pretty quick, but let's see if we can make some sense of this here. That this means that my number of electrons is equal to the density times the volume, right? Which is equal to the density times the area times delta x, and that delta x is the drift velocity times the time here. So in other words, if we go back to our definition of I as being in per time, so I can take this time and bring it over to the other side, divide both sides, then NE per delta t is equal to the density times the area times the drift velocity. So in other words, this is the electron current, is the electron density. This thing has units here of number of electrons per cubic meter. This thing here has units of meters squared for the area, and the velocity here has units of meters per second. So you can see here that really what's happening is that you have a meters cubed on the top and a meters cubed on the bottom, and so you're really left with the units of number of electrons per second. That's really what a current is really all about. So this is the electron current, the number of electrons per second that are moving through. So let's carry on. So take a moment to see if you can answer this question here. Go ahead and pause and take your time, see if you can answer, and then when you think you've got your answer, go ahead and unpause. Okay, we're back. So we have a wire carrying current, and imagine that we know that both the wire diameter and the electron drift speed are doubled. We want to know how much the electron current increases by a factor of. So to do this, we can take a look at our equation that we just found and try to see which things matter. So it looks like the wire diameter is going to affect the area, and the drift speed is also going to affect the current as well. It looks like as either one gets bigger, it looks like we're going to have bigger current. Finally, we can see that the electron current is going to be proportional not only to the area, but also to the drift velocity. Let's pause to work that one out together. I can see here that the current is proportional to the electron density, area, and the drift velocity. That's the average speed of an electron. And you can see that the area, well, you can think of it as pi r squared. Maybe this is the radius here of the wire, right? Or you can think of it as pi times d over 2 squared, right? In any case, area is proportional to d squared. This is this law of scaling that we're going to be using quite a bit actually to make arguments. And we can also see that the current, besides being proportional to the d squared, is also proportional to the drift velocity. So in other words, d becomes twice as much, v becomes twice as much. So now we're going to be doing something where we take d and we put a 2d in instead, square it. We're going to put in a 2 times vd, right? And so the net result is that we're going to have a factor of 8 times d squared vd. So in other words, we've now gone a factor of 8 larger because we doubled d and we doubled the drift velocity. So hopefully that's making some sense. We look for proportionality here. So in most metals, each atom contributes one valence electron, and you can think of it as being a big sea of electrons. And so you can either think of the electron density in terms of per cubic meter or per cubic centimeter if you want to have a little bit more bite-sized units. But at the end of the day, we always like to go to SI units, which is in meters, and that's going to help us to make sense of the. It's going to help us make sense of the figuring out how many electrons there are. So the number of conductance electrons is this Ne is the same as the number of atoms per cubic meter. So in other words, you can see here that there's a lot of free electrons in a cubic meter, and in a cubic centimeter, which you can think of as being approximately 10 to the 6 factor of 10 to the 6 divided by. So in other words, something like 6 times 10 to the 22 for aluminum or so. If you're looking at a cubic centimeter, it's close to Avogadro's number, which is 10 to the 23rd. So we can take a look at aluminum, copper, iron. So you might think that the more electrons that there are, then the better it conducts electricity. And that idea turns out to be basically correct. There are some subtle differences, but that's the basic idea. So you can see that maybe based on this, you'd expect for copper and iron to be very good conductors, but nonetheless, for all 5 of these metals mentioned here to be very good conductors because they have a lot of free electrons. So if you think about how long it should take to discharge a capacitor here, imagine some typical numbers here. you've got 16 nanocoulombs. This means that in a piece of material here, imagine that there's 10 to the 11 missing electrons over here, and there's 10 to the 11 excess electrons over here for this 16 nanocoulomb. Remember, the way that we can do this is we can imagine that each electron is 10 to the minus 19, right, coulomb. And so if you have a certain amount of nanocoulomb, you can figure out how many excess electrons there are. So now, if the drift speed is 10 to the minus 4 meters per second, you'd expect about a half an hour for the electron to travel through about 20 centimeters long of copper wire. But in reality, and as you saw in our demonstration, the capacitor charges almost instantaneously. So what's wrong with our calculation here? So the deal is that wire is already full of electrons. So when you go buy some piping at the Home Depot or something, and you go buy something for water to flow through this your pipe, you have to supply the water into the pipe first. So the idea here is that as some electron pushes in on this side, there's already a bunch of electrons in here, and they automatically push out the other side. So for example, it's like having a hose that's already full with water. If it's not full with water, when you turn on the spigot, then you're going to have to wait for that the water to flow in one side, go all the way through, and come out the other side. So basically, the idea is that this electrons are pushing in. There's already a bunch of electrons, and they push through. So really, it's an almost instantaneous process. So the other idea here is that if you push a book on a table, there's actually a frictional force pushing back. So that's also true with the electrons, is that if the moment we stop pushing the electrons, there stops being a current. So here we have again our picture of two metal plates. And you can see here that when there's no current flowing, the electric field is still zero inside of the metal, as promised, that the electric field is zero inside of a conductor. But what would happen if we push the bottom ends of these wires together? Well, it may not be anymore that the electric field is zero. There might be a flow of current. As the wires are connected here at the bottom, in this very short interval, there's a redistribution of charges. So you can think of it as that electrons are probably the ones flowing in the counterclockwise direction, but we can draw it as a current going in the clockwise direction here. So there is a non-uniform distribution of surface charges that creates an electric field inside the wire. So there is an electric field inside the wire if there are currents. So you can see here that there's a more positive, less positive, and then negative, and then more negative. That's pushing either the electrons to the left or pushing positive charges to the right here. So if we have this situation here where it's more positive surface charge around this area, less positive, less positive, less positive, which direction will the electrons in the wire drift? Go ahead and pause for a moment and see what you think. Okay, we're back. If you had guessed drift to the left, you were correct. So there will be an electric field that points more to the right, which means that there will be an electric force on electrons moving to the left. So finally, this takes us to a concept that's a little bit more practical, which is looking at current. The current is defined as the rate at which charge flows. So instead of counting the number of electrons per second, which is going to be a lot of them, right? We don't want to have to write down that the current is 10 to the 11 electrons or 10 to the 20 electrons every second, etc., right? That's a little bit less practical than just saying, well, how much charge? And then we have this unit called an amp, which is defined as a coulomb per second. So we have a coulomb per second is 1 amp, and that current is the rate of flow of charge. So dq by dt is the rate at which charge flows. So you can relate this to the electron current by multiplying by the charge of the electron. So in other words, if you just multiply by the charge of the electron times the electron current, you'll get the actual current in amps. Okay? So that's our definition for current, is the rate of flow of charge. So let's take an example here. Every minute, 120 coulombs of charge flows through this cross section of the wire. What is the current in the wire? So let's go back and try to figure out what the definition of current is. Go ahead and take a moment and see if you can figure it out on your own. Okay, so I'm going to move to the presentation here, and we have every minute 120. So if the definition of current is dq by dt, then we have 120 coulombs in 1 minute, but really I want it to be in seconds. So 1 minute is the same as 60 seconds, right? So here we have, looks like 2 coulombs per second, or in other words, 2 amps. So if you had gotten 2 amps, it looks like you were correct. So another thing here that we just make sure that we emphasize here is that the direction of current flow, right, which is this purple eye here, we're treating it as if it's positive charges flowing to the left, but we know in reality, the blue line here, is that it's really an electron flow to the right. And so we're going to continue to use the conventional direction flow of current as meaning the direction that positive charges would be flowing, which is exactly the opposite as the direction that negative charges might be flowing. Okay, so another concept that's important and thinking about a charge in a wire is something called the current density. And this is just defined as the charge per area. So this has units of amps per square meter, and you can basically just write this as the number of electrons times the drift velocity times the charge of the electron. So let's just practice it. I think that's the best way to learn, is to try and practice applying this formula to this situation. What is the current density in this wire if there's 8 amps going through a 2 by 2 millimeter bar? Go ahead and take a moment to try and figure it out. Meanwhile, I'll be drawing a picture myself. Okay, so the first thing that we have to do is apply the definition that J is the current per area. We have 8 amps as our current, but the area is a little bit harder to find, so we know that it's 2 millimeters by 2 millimeters. When we multiply those two together, we'll see that it's 8 amps divided by 0.002 meters squared. When we put this all together, we can do it actually without a calculator. If it's 2e minus 3 squared, then this is the same thing as 8 over 4 times 10 to the minus 6, which looks to me as 2 times 10 to the 6. And the units here is amps per square meters. So this is our current density, is 2 times 10 to the 6 amps per square meters. Let's see if we're right here. Indeed, the answer is 2 times 10 to the 6 amps per square meter. Okay, so I think we'll probably start to slow down here, and I might also work one additional problem here. But these 2 light bulbs in the wire are connected to 2 charged capacitor plates. As the capacitor discharges, then the current is through both bulbs is exactly the same. So this is something we've seen in the lab, is that the current that goes through light bulb A is the same as the current that goes through light bulb B. So in other words, the rate of electrons leaving a light bulb is exactly the same as the rate of electrons entering the light bulb. Maybe another way to think of it is that between this negative plate here to this next positive plate here, you can think of it as a highway with no exits, no entrances. So in other words, this idea of conservation of charges is that those charges don't go anywhere. They have to go through this wire. So that means it's the same current at every point in the wire. So let's check this idea here. if we have if we have A and B and they're connected to a battery, which one do you think is brighter? Well, one idea might be that it looks like if the current flows through A and then through B, then maybe A is brighter, and then it's taken some of the energy and didn't leave as much left for B. Or if you think it in the electron picture, that maybe the electrons flow through B and then they don't have as much to give to A. But it turns out that if these light bulbs truly are identical, then the bulbs are equally bright. The reason is because there's the same amount of current that's going through both light bulbs, and if it's the same amount of current, we'll expect them to have the same brightness. Okay, the brightness will be found, we'll have a formula for that soon, but you can imagine that if they are the same current and same resistance, then they should have the same brightness. Okay, so I'm going to go ahead and pause here and then maybe open with one more example problem. Okay, so I think that I'll work problem number 12 in the end of chapter problems. So this is chapter 27, and it is exercise number 12. So just to show you here, maybe I can kind of bring the book over here just to point you in the right direction. We're talking, I can't quite reach, let's see here. So here, I'm talking about problem number 12, which is the current in an electric hairdryer is 10 amps. How many electrons flow through the hairdryer in 5 minutes? That's a good practical question. Let's try it. So the way I would work this problem here, so I'll just say section 27.3. The givens, so basically I have this idea that I have, here's my wall voltage, and here I have plugged into the hairdryer. So this is my hairdryer. It's just an element, and then it goes back, right? So that's my complete circuit here. And I have some current that's going through here. That current is equal to 10 amps. And and I'm not concerned with the details of this wire, in other words, how thick it is or anything like that. I just want to know how many electrons flow through the hairdryer in 5 minutes. So, well, let's see what our definitions are. Our current is equal to basically, let's see here, if I go back to our slides, and I can see that our current is the charge density, or sorry, the electron charge times the IE. And if you remember, IE is the number of electrons per second. Oops, switch back to presentation mode here. If you remember that IE is the number of electrons per second, whereas this here is really measured in amps, and this here is measured in coulombs. Okay, so just to kind of remind you here of what our formula is that we'll be working with. And the charge of the electron is actually 1.6 times 10 to the minus 19 coulombs. Okay, so in other words, coulombs per second, that is amps. So amps is a coulomb per second. Good. So now that we have it set up, this is maybe a little bit easier than we thought. We can see that what we need to figure out is the number of electrons per second. And then if we multiply it by how many seconds, we'd have the total number of electrons. So let's first try to figure out the electron rate of flow. How many electrons per second go by? So if we took the current and divided by the charge of the electron, we can see that we have 10 amps divided by charge of 1 electron, 10 to the minus 19 coulombs. And remember that an amp has units of coulombs per second, so the coulombs and coulombs cancel out, and we're left with 10 divided by 1.6 e minus 19, and this is number of electrons is implied per second is our units here. Looks like I'm going to need a calculator for this one. If I do 10 divided by 1.6 e minus 19, I get 6.25 times 10 to the 19. And this is number of electrons, or I'll just say electrons, that many electrons per second. This is my electron rate of flow. By the way, if you like this calculator, it's called Speed Crunch, and it's available freely online. So we have a rate of flow, and if you notice, if I multiplied this by a amount of time, right, then I would get a total number of electrons. We actually saw that earlier in an earlier slide, that number of electrons was equal to I times delta T. So if we say 5 minutes, well, it's 5 minutes. 5 minutes is 5 times 60 seconds, right? So that's 300 seconds. The current rate of flow is 6.25 times 10 to the 19. That's electrons per second times 300 seconds. If I put those all together, I have that number times 300. It looks like I have a lot of electrons. 1.875 times 10 to the 22 electrons. That's how many electrons pass through in 5 minutes. That is so many electrons. That's a bigger number than I can possibly imagine, but anyway, that is the number. That's how we would solve a problem like that. Trying to think if there's another one. I think we'll be moving on to, I think we've essentially finished, let's do one from section, let's see, I'm going to pause so I can think about it here, which one to do. Okay, I think that's it for now. We have talked about in the lab section that the currents that go into a junction are the same as the currents that go out of the junction. We'll discuss this more next time we meet, and we'll do some more examples. So we'll leave off on this slide here, and that will take us through to the end of 27.3. There are a few points, for example, in your book, you'll notice that there's a model of conduction, which if you find it interesting, I want to encourage you to look through it, but I recognize that it is a little bit more on the detailed side. So since I've not gone over that part in the lecture, I want to encourage you to focus on just the concepts that are in the lecture as a minimum. Hope it was good for you. If you enjoyed the lecture, please leave a comment. If you didn't enjoy it, if you thought it was horrible, also leave a comment. Let me know what it could do to be better. So thanks a lot, and hope you have a good day.